Okay, so hello everyone and welcome to BrainMap. This seminar series is co-sponsored by the P41 funded Center for Mesoscale Mapping housed in the Martinos Center. It's my great pleasure to introduce our speaker today, Professor Andrew Webb. Professor Webb obtained his PhD from the University of Cambridge, and after a postdoc in the Department of Radiology at the University of Florida, he joined the faculty of the Department of Electrical and Computer Engineering at the University of Illinois Urbana-Champaign. He was appointed full professor in 2000 and worked for 3 years in the Department of Physics at the University of Würzburg on a Humboldt Fellowship. In 2008, he was appointed to run the newly formed C.J. Gorter Center in the Department of Radiology at Leiden University Medical Center. He won the ERC Advanced Grant and author over 300 peer-reviewed publications and 4 academic textbooks on medical imaging and biomedical instrumentation. He is an associate editor for MRM and on the editorial board of several other MR journals. Professor Webb is the president of the European Society of Magnetic Resonance in Medicine and Biology. In 2010, he also founded the Nadine Berry Smith Trust, which supports women in science and engineering. I would just like to remind the audience to please address any question you have, even during the talk, using the Q&A box. Professor Webb, thank you very much for coming here today. The virtual stage is all yours.
Great, thanks very much. Thank you for the invitation. I've been sitting down all day, as I'm sure most of you have, so I'm standing up to give this talk. I hope it's not too distracting. So I'm going to talk about 3 different topics here. So basically looking at very, very high field MR, then 2 areas which I know that obviously many of you in Boston are very familiar with. So looking at 70 and then also looking at very low field MR. And essentially, as you know, the sort of title I gave was learning from mistakes that you make all the way through. So I'm going to start with a little bit of kind of an incoherent ramble about some of the work that we did in very high fields, NMR and MRI, and then lead into our experiences, both technical and clinical, in terms of 70 human MRI, and then end up with very low field. So where we are at about 50 millitesla, yourselves then at obviously Matt's group at way, way less than that, and then Clarissa's group a little bit higher than that. So if we have to sum up, you know, in a very succinct way, higher magnetic field simply gives us higher signal to noise. And if we're a spectroscopist, it gives us higher spectral resolution. And that's it. But I think the interesting question, right, is what are you actually going to do with these? What are you going to do with your higher signal to noise? What are you going to do with your higher spectral resolution? I think, you know, as in life, you have 2 choices. You can spend your career running high signal to noise images at 3T, getting beautiful images every time, you know, enjoy life, have a standard family, go to Florida, play what 65-year-olds in Florida call tennis. Or you can take this as a challenge, right? So you can say, given we've got high signal to noise and resolution, what can we actually do? How high can you go and still get useful information? How small can you go with that? What's the smallest amount of material that you can detect using MR? And what's the best spatial resolution? Can you get towards this theoretical limit? So, okay, let's forget about the tennis in Florida, and let's go with the more interesting side on the right. So how small can you go? So if you read textbooks in, say, analytical chemistry, then as we know, you know, the problem with MR in general is it's incredibly insensitive. So if we compare it with other spectroscopic techniques, infrared, mass spectroscopy, then we're orders of magnitude less sensitive, just from intrinsically, because we've got this Zeeman term in our energy levels, and there's just so few, that the splitting is so small, and we can only detect that excess in the 2 energy levels, that intrinsically we're way down. And so typically we're of 5 nanomoles, something like that. So if you've got a sample and you want to run a high resolution NMR spectrum, people will tell you need 5 nanomoles, it's going to take overnight. So we thought, let's try and address this issue. So we want to go to very high field. So we have access up to, say, 950 megahertz. Now we can go over 1 gigahertz. How do we get the maximum sensitivity, well, we make the coil as small as possible. And so this is going to the extreme, right? This is the 1 cent that's in all of your pockets at the moment. And so this is a coil here, which is less than 150 microns in diameter. So we're going to take a sample and we're going to concentrate it as much as we can. We're going to put it inside this very, very small coil. And then, of course, if you're a high resolution NMR person, you know that you've got to be able to shim that to less than 1 hertz. And we know about susceptibility, right? You want copper right next to your sample. So it's not just a question of building this coil, you then have to do a lot of tricks to get high resolution spectra out. But if you do this and you take the challenge, then rather than 5 nanomoles overnight, you can then start off with 1 nanomole, and it took us 1 minute to get the spectrum. And if you look very carefully over here, you can see these are the anomeric protons on a glucose molecule, and those are split. And that means that your resolution here is essentially sub-hertz. And let's take it further and look at, well, why would we want to do this from a practical point of view? We can take it from nanomole down to picomole. And this is some spectra that were taken from a combinatorial chemistry experiment where you basically synthesize tens of thousands of compounds in very, very small amounts, and you want to get the NMR spectra. You can't do that if it's going to take forever. And so here we are down at the picomolar level. And this is new areas for MR. We haven't been able to see this. And then you give this to the biochemists, and what they're interested in is natural products at very, very low concentrations, very low amounts. So here's one example where people here were looking at fireflies and looking at steroids coming from 1 or 2 fireflies. So very, very mass limited samples. So that's one way that we can use very high field MR. And we do imaging. So we might say, well, what can you do in terms of resolution? And this slide sort of, I think, puts things in perspective. Here's our normal, let's say 3T MR, running at about 1 by 1 by 1 millimeters in terms of the resolution. Take 1 voxel out of that. And if you want to go down to 4 by 4 by 4 microns, that means our scale is 256 by 256 by 256. So our volume that we're trying to interrogate now is 16 million times less. And if you work out what that is in signal to noise, and then corresponding to time, right, you get an enormous amount of time that it would take without increasing the sensitivity. So what can we image? If we can go down with these very small coils, we can start to image single neurons. So this is a well-studied biological system in Epilepsy, Californica, looking at an L7 neuron. Now, to be honest, imaging is completely pointless at this thing from an MR point of view, because optically you can do this much better and you can do this much quicker and much cheaper. But what you can't do optically, of course, is look at the chemistry inside. You can't do spectroscopy, you can't make diffusion measurements. And so here you can see within the nucleus of a single cell, taken within 8 minutes here, you can get ideas about the concentrations of biochemicals in there. And you can see what happens when you give challenges to that. You might give ultraviolet light, you might give chemical challenges to this, and we can see what's happening to the intrinsic biochemistry. And we're continuing this work. So this is with my colleague here, it's Ronan, and you can look at organoids. So organoids, this is the organ on a chip. This is trying to get away from animal experiments. This is really sort of cutting edge research that's going on in a lot of tissue culture places at the moment. And again, what we can do then is to image these, and these are typically much less than a millimeter in size. But more importantly, we can start to get biochemical information. And again, here we are going up to 900 megahertz, and we should be soon going up to 1.2 gigahertz when that machine arrives in the Netherlands. As we're building these coils, we realize it's quite difficult to build everything at this very small scale. You have to be very, very careful about how you're winding the solenoids. You've got susceptibility issues. And so this also forced us to look a little bit into different kind of probes. So one of the common themes that's going to come through here is kind of like dielectric materials or ceramics. And so working with the group in Russia then, we're able to increase our sensitivity even further by taking very conventional coil designs and changing that so that we really have here just a piece of ceramic. And that piece of ceramic stores a magnetic field in the middle, and there's no electric field in the center there, which of course means for conductive elements that that's going to increase our signal to noise. And so if you compare what everybody else uses, which is a solenoid, with one of these ceramic resonators, and this is work done with Louisa Ciobanu in Paris, we see a significant increase in signal to noise over here. So by going to high field, by looking at some new elements in terms of the RF here, we're able to get really incredibly high resolution or study very small amounts of material. But when we talk about high field, I've said, okay, we're looking at 21, 22 Tesla, something like that. Let's really go to really high field. Let's push it as far as we can. And this is work that I was doing with the Leibniz Institute in Dresden, full of some completely and utterly insane German and Russian chemists there. And essentially what they had here is a 60 Tesla superconducting magnet. So we're going to do 60 Tesla MR. The only problem is it's a pulse magnet. And that means essentially you put a lot of energy into this. It goes up to 60 Tesla and then it comes back down again. And it does that in about 20 milliseconds. So you take your magnet here, you put it in a large bath of liquid helium over here, and then we use a capacitive discharge to take that, that field from 0 up to 60 Tesla. But this is no normal capacitor, okay? This is probably the largest capacitor you've ever seen. So this is a 50 megajoule capacitor storage bank that is in the room right next to the MR machine. So essentially our experiment is the following. We have to cool down the magnet. We have to discharge 50 megajoules, which means that in Dresden, the lights literally went down for about 3 seconds when we do that. The field is going to go from 0 to 60 Tesla and back down again in 20 milliseconds. And we have to time it exactly so that our coil, which is tuned, I'll explain why in a second, at 56 Tesla, gets the FID there. So obviously, you build absolutely everything yourself for this system. And then these are the results that we got out. And again, some of you will know Mikhail Kozlov over here, who was the person who really designed a lot of this electronics. But you can see here that as the field is going from 0 up here, we managed to catch it so at exactly where it needs to be with the coil. So we're catching this as a 56 Tesla. Our coil is low Q, so we can actually catch it a little higher over here. And then, of course, since it's going to take, our TR here is about 5 hours because the magnet has to cool down from about 300K all the way down to superconducting again. And so we catch it on the way down over here. And so here we're able to actually measure some relaxation times, believe it or not, even though this is on the millisecond scale. And this was some work we were doing with the solid science chemists over there. So after all of that, 70 human, how difficult can it be, right? It's not like you're trying to explode your magnet. You've got this massive human in there. You're not looking at single cells. So in coming here and starting our group up on the 70, this is going to be a doggle, right? And then there was a few things that started to, come in, questions. What do you mean SAR? What is SAR? Who cares about SAR? Why is the sequence not running? Why is the Philips telling me I can't run a turbo spin echo with 5,000 echoes because of this thing called SAR? And yeah, stop moving, right? If somebody gets in the magnet and they start moving around and you get image artifacts, so dealing with humans. And why are there black holes in the image? Why is the temporal lobe here black? So which idiot built the coil here? And then, spectroscopy, everyone's going 12 hertz line width. This is great. I mean, you gotta be kidding. We're used to sub-hertz line widths, okay? So all of this, of course, is trying to translate the knowledge from other high field work to the human field. And there are lots and lots of things that we just hadn't considered. And there's lots of things we have to try and solve. And we also have to get somewhat realistic about what our aims are. So of course, if we look at this black holes in the image, right, this isn't which idiot built the coil. This is the fact about physics, that as we have now a wavelength somewhere between 12 and 15 centimeters, we get constructive and destructive interference, right? And so we have central brightening here, but we have low intensity out here. And temporal lobes are kind of important in a lot of epilepsy, let's say, or in dementia. So this is just a physics problem that we have to overcome. Increased SAR, heating at 7T compared to 3T or 1.5, are not only just increased, but also the spatial distribution, of course, is very difficult to tell. And so this is work, of course, by Chris Collins here. And again, if you're at 3T, then things act sort of the way you expect. You know, your electric field is going to be 0 in the middle because you've got a very symmetric structure. If you're driving with a birdcage, you know where the heating is going to be. Yeah, that goes out the window when you start looking at 7T here. So you can get hotspots in different places. And of course, this means that you have to set up quite a sophisticated modeling program here. So we've had Vika Brink and our group doing this for many years, so that we can model everything and be doing everything with a high degree of safety. And of course, yeah, does it work first time? You come in, I mean, you paid 8 million euros or $10 million for this magnet. It better give you images, nice images first time. So, you know, here's our first cardiac image that came out on the left. And then we were going to image eyes. I'll talk a little bit about that later. There's the ocular image and the neuro image again. As I said, it's got these large dark areas. So sequences have to be developed, problems have to be understood. But if you do that, then you can end up with images like this, where we're looking here, then at the inside the heart, we can see very good depiction of the vessels. This is an ocular tumor here, so we have excellent 3D images here, showing in this case there's a necrotic core inside that tumor. And then neurologically, of course, we can get whole brain coverage here, in this case just for an angiogram. So what did we have to develop, and what did we actually learn from the previous work on high field? Well, the first thing is, how are we going to steer and focus magnetic fields? So one of the problems, of course, is that the RF interferes with the conductivity and with the permittivity of the body a lot at high field, much more than at low field. But it also gives us an opportunity to steer those by saying, if we take dielectric materials, materials with high permittivity, we can start to reshape the magnetic field and indeed the electric fields, right? So what we can do then is, we know that this problem is going to get worse and worse. And again, this is just basic physics. So we start to say, let's form some high permittivity material. So these are just 2 pads over here. This is made of calcium titanate, so epsilon about 100. And essentially, we simply take all the software and all of the hardware standard on the system, and we just add these dielectric pads to the left and right. And then the theory behind this, of course, is that we're going to look at, in a high permittivity material, it has displacement and conduction currents. So displacement currents are what we want. In other words, we have the electric field that is produced by the birdcage coil over here, is going to interact with a high permittivity material. That creates a secondary magnetic field. And if that secondary magnetic field can fill in the space here, the dark areas in the temporal lobe, then we're going to get towards a more homogeneous and more uniform contrast. You also get conduction currents, and conduction currents are not good, because these are they're effectively like eddy currents inside the body, so it reduces the total magnetic field. So what we want, of course, is to have that the displacement currents here are much higher than the conduction currents. That means we want to be at high frequency, so that's great. And we also want to have high permittivity in terms of the material. And so by using this gives us a pretty easy, pretty cheap, very practical solution, let's say, to some of the signal dropouts in neuroimaging over here. Now, of course, so for about the first 3-4 years then, this is what we did. And everybody was scanned with this. And it's interesting, actually, now, as you know, the Siemens Terra is the first FDA-approved scanner, and they actually ship out these dielectric pads with the Terra. But of course, as your group knows, this is not a complete solution. And of course, if we can come into parallel transmit, then we also have a very, very flexible way of addressing this problem. And so using this, let's say parallel transmit and some pulses, universal pulses in this case, or some other KT spokes pulses, again, you can overcome the intrinsic inhomogeneity here and start getting really whole brain coverage. So the SAR problems and the B1 problems are manageable. Motion is kind of an interesting one. So what we found early on is being in a hospital here, the idea is we do clinical research or we even do patients here. And what we saw was, having put into place all of those improvements over here, we were getting beautiful images in volunteers, and then Alzheimer's patients came in, and you get images like this. And all of the detail, everything you want to do, you want to be looking at QSM, other measures like that, totally impossible because of the artifacts, the image artifacts. So you think, well, this is probably because the patient is moving, but we don't see any gross effects, you know, outside, which you would expect. You'd expect to see some ghosting in the phase encoding direction. You just don't see that. So what's actually going on? Well, it is motion. And if we put on a respiratory belt here for a normal volunteer, you see this regular breathing over here. If you look at an Alzheimer's patient over here, you see, well, more rapid breathing, probably just due to age, but you also see large jumps over here. And what I plotted out here is actually the frequency in the brain. So this is looking at what is the water resonant frequency in the brain. And it's jumping. And it's jumping not because the head is moving, it's jumping because either the breathing is changing or some other part of the body is moving. And that means that you get changes in the brain, and this effect is supralinear with magnetic field. This you're really not going to see at 3T. So literally, if somebody is moving their arm up and down, it will produce a measurable frequency change in the resonance in the brain, which of course suggests that actually this is quite easy to fix, right? Because we can simply do some navigator echoes, and we can look at what's the phase of each case baseline, and we can just phase shift it. So this is what we did. And again, you can then see significant improvement from this person here to after correction. And the nice thing is everything is post-processing. So you can try it out, and then if it doesn't improve it for whatever reason, you still have the original data. And so we take this one step further. Of course, this is assuming that this F0 change over here is uniform, is everywhere. But of course, we have much more information than that, right? Because we have all of our receive array coils. And we can look at the phase in each of those coils. We can see those changes. So we don't have to just make a uniform change. We can actually make a much more localized change to case-based. And if we do that, we can move over here. So here's with no correction over here. We apply uniform correction. We apply one here that is just based on the receive array. And here we actually put some frequency encoding information. So it's a 1D plus the receive array. And you can see you can go from really a horrendous image over here with artifacts to almost complete recovery of the information over here. So put everything together and you have a system that can potentially be used clinically. And so we over here then concentrate on 3 or 4 different applications in the clinic. So the first one is epilepsy, which a lot of 7T sites do. And if we look over here, this is a 3 Tesla scan. There's a cortical dysplasia here, which is not easy to pick up, which is actually initially missed by the radiologist, but clearly the signs are there in terms of the patient characteristics. And so when we took the same patient at 7T, again, here's where your extra signal to noise really comes in. And you can see here where the arrow is, we can see this over here. This is the dysplasia. It's a characteristic sign of it. It points in towards the center of the brain. And, you know, if you go back onto your 3T, then maybe you can make it out. But the confidence that the epileptologist would have in making that diagnosis is far, far higher at 7T, again, simply because your SNR is allowing you to make thinner slices, higher spatial resolution, and that's increasing your contrast to noise ratio. The other areas that we use a lot is oncology. So this is looking at lesion detection in the optic chiasm. And again, essentially what you're looking at is something very, very small down here, which again, possibly is visible on the 3T, but again, the accuracy or the robustness of that is much less. Second example over here, which is even more demonstrable. So you see that white lesion in the middle there, which you simply can't see at 3T. So this is where 7T, if you can get rid of a lot of those artifacts and scan safely, really has an advantage. And one example where it actually is used in patients and that the results have an effect on diagnosis is looking at eye tumors. So uveal melanoma is the most common eye tumor. It's a horrific disease, mainly because the eye tumor will metastasize. So it's in the eye, it breaks through the back of the eye, it then metastasizes, and most patients die of liver cancer within about 6 months. And so it's something where enucleation, in other words, removal of the eye is often used. But there are other options, because of course you would like, particularly in younger people, to maintain that sight. So you can do brachytherapy, so radiotherapy, by placing a plaque here with radioactive elements at the back of the eye. And obviously how effective that's going to be depends on the size of that tumor. If that tumor is too big, this plaque is not going to be able to irradiate at the back of the tumor over here. And so you have to resect. And there are certain size regimes, knowing the plaque size or the maximum plaque size, that if the tumor is bigger than that, you simply take the tumor out. And if it's smaller than that, then you go first for brachytherapy and see how that goes. And the standard way that this is done is with ultrasound. So this is, you can see high resolution, high frequency, probably 10 megahertz ultrasound transducer on the eye. And the kind of images you get out are like this. And you can see the problem here is that the ultrasound is very low contrast. It's quite difficult to see where the tumor hits the back of the eye. And also, of course, ultrasound is 2D, and it suffers from refraction. So any small changes in the angle of that ultrasound transducer are going to change the apparent size of that tumor. And you can see here are 3 patients who came through our clinic. The number that we use, threshold for enucleation versus radiotherapy, is 7 millimeters. So this one is right on the edge, right? 7.5 millimeters. So this patient would have the eye removed. So the ophthalmologist approaches and say, okay, you've got a 7T, you've got high resolution MR. We'd love to put our patients through this and actually get, if you can assure us that you can get a better diagnosis, a better measurement. So of course, not that easy to do, but you build your own coil, right? So you have to, again, go through all the safety checks, things like this. So here's an eye coil over here. We're going to have to scan for a couple of minutes, which means the patient's going to blink. We can't afford to have any motion there because we're going to be looking at small tumor volumes. So we have what's called a blinked, a cued blink protocol. So we acquire part of case space, then the patient blinks, then we go ahead and ahead. And so this is all work done by Jan Willem Beenakker in our group. And you can see you can then get pretty high resolution 3D images of this tumor that allows you to get very accurate measures of the tumor shape and size. And so if you take these patients, these were the couple of patients, and one of them clearly 10.7 millimeters is an enormous tumor that has to come out. What we know though is ultrasound tends to, not in all cases, but tends to overestimate the dimensions. And so when we looked at patient number 1 on the left here with the MR, that tumor actually was measured to be 6.2 millimeters, not 7.5 millimeters. And so this meant that actually the treatment plan for that patient changed from removal of the eye to brachytherapy. And this is a patient for which that tumor has actually shrunk considerably. You don't get full eyesight back, but at least you have partial eyesight. And also, if you're young, which tends to be the age group where this is effective, just having your eye physically there, rather than having an eye removed, is an incredible psychological boost. So here's an example where this really high resolution that we always think about in terms of MR actually has practical clinical relevance. And there's lots of other clinical things that I could go through in terms of high field MR. So we've got the 7 Tesla, and then maybe 10 years ago, a colleague of mine came up when I was working at Penn State, and he's a neurosurgeon, Steve Schiff, who's known to some of you, and essentially he's a pediatric neurosurgeon treating kids in Uganda, and he said it would be fantastic if we could get an MR system that was cheap and portable, and I could use for pediatric hydrocephalus. Is it possible? So low field MRI, how difficult can that be, right? I mean, you don't have many of the problems that comes into high field. So we start to build some low field. First question, what happened to the signal, right? I mean, we're 50 millitesla versus 7 Tesla, big difference. So you have to find where your signal is. Then never thought about this, never had to think about this before, right? My coil bandwidth is too low. My coil Q is too high. That's a thing I thought I'd never say. But the coil bandwidth is less than the imaging. So what are you going to do with that? I really appreciate having a shielded room for the other magnets, right? Because here's a magnet that's got to go around. We did operate in an unshielded room. So you've got noise coming in from all sides. And then forget 12 hertz. This is like 1200 hertz line width. How are we going to deal with that? So again, lots and lots of things that are completely opposite. And all the solutions that we come up with a low field are essentially the opposite to what is at high field. And that sounds obvious, and maybe it is obvious, but certainly a lot of these things were really a surprise coming in. And you sort of think, am I going to be able to cope? Am I going to be able to use standard techniques and conventional techniques to be able to try and deliver on, what this sort of challenge that Steve came up with? So the target, as I said, is pediatric hydrocephalus. So it's a buildup of CSF. We're not trying to diagnose it. That's easy. What we're trying to look at is after it is shunted and that fluid is removed, is there remaining CSF, and particularly is there blood in the CSF, because that's rather dangerous. So our target resolution is relatively low, which is good, right? Because we're going to be at low field, low signal to noise. And these are the partners. So this is the center in Uganda, and these are the other people who we work with over here. And of course, that also got us thinking about accessible MRI, right? It's nice to have a 7T, it's nice to have 1.5T, but if we actually look at the role of MRI in healthcare worldwide, we can see this in terms of vaccine rollout now. 70% of the world, this is irrelevant. They don't have the resources for any kind of MRI. And the question is whether these kind of low field systems could potentially start to help in this problem. And the challenges are effectively this: the purchase cost is in millions, but that isn't the biggest problem. At each place, getting some money for something is not necessarily the biggest problem. The issues come in annual maintenance, hundreds of thousands of euros, as we all know, recurring costs all the way down. And it's got to be sited, right? It's got to be in a shielded room. It's got to have high power. It's got to have high fidelity electricity lines. You can't have power cuts every 3 hours. You've got to have chilled water. You've got to have this, that, and the other. So all of those kind of things that A, cost an enormous amount of money, and B, of course, are not very available. And then running an MRI machine, it's difficult. We have highly trained techs. So we have to look at something that is going to try and address all of these points if we're going to build a system. And also, while we're doing it, let's think about the sustainability of this kind of approach. So this is the world's most sustainable smartphone. It's called the Fairphone. It's actually produced just up the road here in Utrecht. So what does it mean by sustainability? Well, recycled and fair materials up here. We can have a go at that. I'll say something of that right at the end. But it's designed to last. In other words, it's modular and it's repairable. So as we start to design our system, we want to do the same thing. When a system is in Uganda, is in Malawi, and it breaks, it can't just sit there. That's what 95% of donated medical equipment does. It sits there because nobody can fix it. So we need to be able to train people to be able to fix what we send. So what's the challenge? Okay, we know it. B0, 7/4. We're down by a factor of 300 compared to 1.5. So let's just push that to one side and let's be positive and think about the advantages of low field, right? So one, okay, already said it. Lower siting costs and obviously far lower purchase costs. Think about magnetic susceptibility. So in terms of air, whether that's in the lungs, nasal cavities, etc., much less. Much lower artifacts from medical implants. I'll show you that. And not just medical implants, things like blunt trauma, things like shrapnel in the body, etc. SAR, we almost don't have to worry about. Contraindications, again, if things are in the body, whether that's medical or that's coming from violence or other things like that, then this longer critical wavelength, right, the λ/2 inside the body, means that we really don't have to worry about RF heating from that point of view. Gradient noise, it's almost silent, not quite, but it's pretty quiet due to our reduced Lorentz forces. And then, you know, as in our NMR physicists here, we know that dipole-dipole coupled systems are going to have a shorter T1, and we're going to have a longer T2 star, and we're going to have a reasonable long T2, which means that our readout sequences can be much more efficient. We can do enormously long echo trains for TSE, we can do large spirals, things like that. So there's ways from a pure MR point of view to grab back some of that signal to noise. And of course, we're aiming at lower resolution, which in itself is going to give us some signal to noise per pixel back as well. So very low field systems, you know most of these, right? I think, you know, Matt's system over there was really the one that when we started thinking about this gave us confidence, or a degree of confidence, that this was not going to be a wild goose chase, right? If you go 6 millitesla and you can get those amazing images still from Mathieu Saracani, you know, back in 2015 or whatever, they're still amazing to look at, thinking this comes from 6 millitesla. So we may make lots of engineering mistakes, but the basic physics is there for us to be able to get signal to noise. And then we look also at Clarissa and Larry's setup over here with the Hallback with the built-in gradient. And again, really nice high signal to noise images coming out of that. This fascinating system David Lurie's constructed in Aberdeen, which is this field cycling. So it jumps from anything from 50 microtesla up to 200 millitesla. So you can really choose your image contrast that you want to look at. Of course, you've got hyperfine over here with about a 60 millitesla system. Again, some different magnet design. And then our own one over here in Leiden, which I'll talk a little bit more about, built by Tom O'Reilly at 50 millitesla. And so one question that comes up here, actually, if you look at this, is why is it that every single low field site is within 5 kilometers of the sea? I'll see if anybody has an idea of that in the question and answers afterwards. And of course, there are mobile units. Then the Tsukuba University in Japan shows the portability here of an extremity scanner at 200 millitesla. And what we'd like to do is ideally take our much larger head imaging system and have that degree of portability that they showed. You've seen these images before, definitely. This is Clarissa's work just published in Nature Biomedical Engineering. Again, with the inbuilt linear gradients in the Hallback there. And again, signal to noise really pretty impressive. And this is around about 80 millitesla. Hyperfine, of course, is lower. And although it's portable, you know, this thing is 700 kilograms. So portability is in the eye of the holder. To get around a hospital, it's perfect. It's on wheels. It's very elegantly designed. It's got very easy access for patients over here. And of course, if you want to study people in the ICU or had a stroke or anything, it's really a revolutionary design here. And again, the images coming out, if you think about it from 58 millitesla, pretty impressive. I mean, these look like 1.5T images, you know, probably in the mid 1990s. And a lot of work now beginning to come out showing this operation in the clinic here. So Kevin Sheff, also the people at Yale, imaging, studying image, a lot of people here. And what you see, I think, is you see the good side and the bad side, right? You see that some of these images are really, really pretty impressive here. And you see when we look at diffusion, then there's a way to go. And that's great, right? That technically everything looks good, but it's not as if every problem has been solved. And of course, then a very similar design then coming from China over here, also looking at stroke patients with the 50 millitesla here and comparing with CT. So we took a similar but slightly different approach to what Clarissa did in terms of the Hallback array. And when we started actually reading those papers, initially my thought was, okay, this is a very clever approach because you're not trying to do something that is very difficult, which is to make a homogeneous field, right, on a relatively small magnet. And maybe it's much easier to put something with a linear gradient. Maybe if we look at the equations there, that is really the way to go, and we need to do that. And then Tom basically said, hold on, let's have a look and see what we can get in terms of homogeneity. Okay? So the Hallback array, you know, and of course, you know, Beta Blumler down here essentially has thought about every single design of Hallback that there is. So really kind of a visionary in the field. And of course, he was applying most of this to chemical applications or plant applications or hyperpolarization. So everyone has been taking his ideas and basically scaling them up. And so here's what our system looks like. So again, we were trying to think here, not only from the point of view theoretically getting the best magnetic field, but suppose you want to manufacture this. And supposing even more so, you want your sister site in Uganda to be able to manufacture this. What can we do to make that an easily and trainable approach? And so rather than using very big magnets, which will give us a stronger magnetic field, we used smaller magnets simply because A, they're safer during construction. It means that we can get some finer optimization. And since we're buying relatively cheap magnets, which are going to be plus or minus a couple of percent, it averages out. If you're going to use several thousand in a magnet, that averages out those imperfections. And so what Tom came in to do here is basically to look at a genetic algorithm to try and optimize the layout of these, to try and get as homogeneous a field as possible. So here's the system that he came up with. So effectively side view here. So we're looking at, again, pediatric brain here in terms of being able to image. We have almost 3,000 magnets here and the magnetic field about 50 millitesla. So we're operating 2 megahertz. It's kind of interesting. This is, you know, it came also from a lab that used to do a lot of ultrasound. And this is exactly the frequency that they're operating at. Obviously, mechanical waves rather than electromagnetic waves. But a lot of the hardware that they've developed actually is kind of useful for considering how we're going to design things. So the magnet here is up and constructed. So you see B0 field, of course, as you know, which is transverse, which means as we design RF coils and gradient coils, we have to take that into account. And from the gradient coil, it's going to give us a slightly different approach to what we're using in terms of the target field. The measurements looks like the simulation, but it's, of course, in terms of magnitude, the measurements is a lot poorer. And this comes from a number of different causes. So simple displacement errors, maybe some demagnetization effects of magnets being very close to each other. And of course, there is variation in that magnet quality. So this was not unexpected. We're quite glad actually to have the general shape there. So of course you can come in then and shim, and you shim the old way that people shim, which is putting in very small permanent magnets. And again, you can use the same kind of genetic algorithm then to come up with the placement of those, whether they should be in one direction, another direction, or no magnet at all. And so that's another 660 magnets for Tom to put in place. And the results of the shimming then show a significant improvement in terms of the ppm. And again, you can see here, this is the field distribution. So your field gets a little bit higher, which is great because you're adding more magnets there, and the distribution becomes a lot narrower. So now you really have a system which is usable, right? Which we can think about with a reasonable gradient strength, we can actually get quite high resolution images. Because although 2,500 ppm sounds awful, particularly when you come from NMR, where you're talking about parts per billion, when you transfer this into absolute frequency space, and we think about the value of the gradients there, then we can see that we're not really, until we go to very, very high resolution, we're not going to be delta B0 limited in terms of that resolution. So we add in the gradient coils, and the gradient coils, as I said, we use the target field approach just because it's easy for this kind of very analytical shape. Of course, you can use boundary element methods, and as we start to go to more complex geometries, that's exactly what we're going to do. And so you know the target field approach here. You essentially define the gradient that you want here. You work out what the surface current is, use stream functions then to discretize those for the wire patterns. The mathematics is a little bit more involved. So this is Bart de Vos, who has designed this. But essentially then, by including extra terms, so you have extra cosine terms that come into this, these equations for stream functions, you can realize the gradient coils here. And again, obviously in this case, Y and Z are the two which are rotated by 90 degrees here. And these are all 3D printed. So this is a standard 3D printer over here. And then again, standard wire just pushed into those formers. And the forces are not strong. So again, we don't need to go into any significant amount of epoxying, etc. And RF coils are fairly simple, right? Solenoid is what you want. It's highly sensitive. It's got a pretty uniform B1 field. We can improve that B1 field by having the wires slightly closer together on the outside and then slightly less close together on the inside. And of course, we've also decided to steal the design then coming from Matt's and Charlotte's lab. And for most of the brain studies, we use this spirals version of the solenoid. And this really helps, of course, with signal at the top of the head here. So one of the things, of course, we're having design coils now for, from 56 Tesla, now we go all the way down to, 50 millitesla. Here's your coil unloaded, and here's your coil loaded, right? It really doesn't make any difference if you design it well. And again, you come to this bandwidth issue, right? So the bandwidth here is 20 kilohertz. Your Q is maybe about 100. And 20 kilohertz is not a big bandwidth to be considered when you're imaging. So it's one of the things that we have to consider. Others, of course, have considered this. Greg Scott has a large thesis on this. But it was just one of those things that coming into this, we hadn't really thought about too much. And so for the rest of the plate, then we have the gradient amplifier, RF amplifier. Again, these were designed to be easily repairable, to be modular. And these are costing roughly $1,000 each. And everything here is open source. So this is the other thing that we wanted to try and do. So if other people want to build hullbacks using this optimization, they can go to GitHub and you get Tom's code is there. If you want to design your gradients based on the target field, Bart's code is there. If you want to go in and you want to look at the RF amplifier or the gradient amplifier, then the schematics are there. And we've had a number of sites then around the world who have looked at these and downloaded various of these. So again, the idea is let's try and make things sustainable. And also if improvements come in from different places, that's great. So here's our integrated setup. You probably very similar to your own. We're not in a shielded room, I think, unlike Clarissa's setup. And so we have built just an aluminum frame around here. And in order to sort of simulate that shield, then we have a conductive cloth then that goes over the body here and just connects over here to the shield. So in terms of sequences, then we tend to use turbo spin echo sequences simply because they're high efficiency. We don't have to worry about SAR. T2 is relatively long compared to T1 at higher field. Other things we've just built in is some model-based B0 non-uniformity correction here. So this is work by Kirsten Kolstra. And effectively here, even if you've got quite severe artifacts, now this one came because we actually stuck a magnet out here. So we couldn't make the artifacts bad enough to really show how well the algorithm worked. So we stuck an extra magnet here. You get significant distortions. Again, if you look at the model-based approach here to correct for B0 and also can do for gradient nonlinearities, we can get back to decent images. And so what we've been doing, or Tom in particular has been doing, now we have a good high quality set of data, is to do some relaxation time mapping. And this is essentially, there's many old papers. David Holtz has the classic paper. Bill Rooney has some papers on relaxation times as a function of frequency. But the data are quite limited and often extrapolated. And of course, in Bottomley's case, then most of them are ex vivo and a lot of it is animal. So in terms of quantifying relaxation times, which are going to allow us to optimize pulse sequences, but also potentially allow us to do some segmentation of tissues, then getting accurate measurements is important. So this is some of the data that Tom will be presenting at ISMRM. So looking at T1 maps, here in the brain, looking at T2 maps, everyone always asks, why do you have a big distortion over here? The answer is that's me. If I put my head down, which I'm not going to, you will see exactly the shape of the head and the brain over there, the pointed. So there isn't an artifact At least maybe it's a physical artifact, but it's not an artifact of the imaging system. But T1, T2 maps can come out, and then these can be quantified in terms of white matter, gray matter, and then the lipid. And you can see this forms quite a nice basis for doing an image segmentation. And again, there is nothing else going on here. This is no AI, this is no extra information. That, of course, is a completely valid approach. But at the moment, we're simply doing this off raw case-based data. We're also very interested in muscle, not just brain. The idea of being able to do exercise, really do exercise inside a magnet is one of the great things, research point of view, of low field. Heming Khan in our group is very interested in that. So again, here's T1, T2 maps in terms of the muscle. And as one would expect, the segmentation here is simple lipid and muscle, but again, showing very clear definition there. And so what we can do in terms of exercise is start to look at changes in the T2, which come from muscles producing edema in a much, much easier way than having to build an MR compatible bicycle and stick it inside the magnet. And then it's interesting to look at these measured times over here from Tom's work, and to go back to the work from Bottomley in 1981. And what we see is many fall certainly within the standard deviation, although there's quite a large standard deviation in Bottomley's work. A couple of things lie outside it, but essentially the results we get, I think we have a high degree of confidence in the sense that they agree with this and some of the other models that people have come up with. So one area we've also been looking at then, because clinically we want to use this, is this safe? So everybody says low field is safe, but you can't just say that, right? If you go to your IRB, you're going to have to produce some data. So we've been measuring with Camille van Speebroek here. We've been looking at forces on implants, so things all the way up to glucose sensors, right, which you would never put inside a 7T. But if we look at the forces there, then of course they're orders of magnitude less, as one would expect, but this actually gives you some quantification. And also in terms of image artifacts in medical implants, even if the medical implant is safe, it doesn't mean that your image is going to have any diagnostic use whatsoever. And so she's been looking at different kind of clips over here. So it's interesting, if you look at this, this is an iliac stent, goes around one of the vessels. And you can see significant artifacts here at 1.5 and 3 and 70. You can hardly pick it up at 50 millitesla over here. So again, if you look at a screw where it completely destroys over here, you can actually see the turns and the pitch of that screw at 50 millitesla. So this is nice again to be able to quantify for ultimately using in patients with medical implants. So that's sort of state of where we are. So what are we doing? What do we see? What is kind of interesting to look at in the future? So I'll start off with one thing that's completely non-obvious, and that's to do high resolution spectroscopy. And then, right? High resolution means like 1 hertz spectral width. Here's the spectrum, which is 500 hertz. Maybe it's a kilohertz. So how are you going to get any kind of information out of that? Well, again, what we start off with is to start off by looking and saying, well, what would a high resolution spectrum look like at this field strength? So here's a standard. If we look at lactate, for example, we have a quartet and we have a doublet from the CH3 and the CHs at 7T. What would that look like at 50 millitesla? And the answer is completely different. This is what is called strong coupling, because our delta chemical shift here then is comparable with our scalar coupling. And that means the spectrum becomes a lot more complicated, but there's a lot more interactions between those. So that's kind of interesting. So what we can do is go back to some old ideas in terms of perfect echoes and J refocusing. And essentially what it says is that if you consider like a CPMG train, and we're going to look at that signal decay, that's going to be modulated by T2, not T2 star. And that's going to have also going to be modulated by this strong coupling. And so if you look at that decay and we Fourier transform it, we look at our frequency axis down here, you can see we have sub-hertz resolution. And if you look at lactic acid and we have a simulated spectrum and we have the real spectrum here, then we can see we've got very good agreement. So you can potentially pick up lactic acid spectroscopically here in a very, very inhomogeneous field. Other things are working. So Jason Stockman, of course, is one of the pioneers here with Thomas Witzel in terms of Okra, and we're looking to try and integrate that into our setup. We also have to look at, again, external noise sources. We have to look at changes in temperature. We know the temperature changes. At the moment, we assume it's linear. In other words, it's homogeneous everywhere within the magnet. That probably isn't true. So we'll be looking at temperature sensors and then how to reconstruct those. So one simple example is to say put 16 and then do third order spherical harmonic distribution, correction. RF coils, yeah, at low field, we want to do phased arrays, not for signal to noise, but so that we can use very high Q coils, impedance mismatch into the receiver, and not lose sensitivity there. But of course, the problem is that there's very low coupling to the body, which means that phased arrays then have much stronger intercoil coupling. And also, even if we connect them to low impedance preamps, these are not really very available. So 2 ohms really isn't very low impedance when you're dealing with this degree of coupling. And so Javed Praza in our lab has started to work on these. So you can see the coils over here with an impressive half of our supply of non-magnetic capacitors here. And again, you have to change you can't just use surface coils all the way around. You have to use butterflies and loop coils, etc. And so in initial results then, he's been with a 4 coil array, again, using a fairly simple sum of squares distribution here, then we can get a reasonably good image here of the knee and then all of the individual components over here. Compressed sensing is another thing that we've been doing. It works fine. And in terms of things like fingerprinting, it's interesting that fingerprinting works, but if we look at low field, the ratio of T1 to T2 is very, very different than it is at 3T. And what this means effectively is that the optimized flip angle train becomes very different at lower field than it is at higher field. If you do that, then you can still get very good results potentially from fingerprinting. We're looking at lots of different designs here. You can actually see some magnet rings right behind me here. We're designing then some dome-shaped magnets. And of course, this is very much along the lines that Patrick has done in Larry's group over there. Again, we're going to aim for a very homogeneous field. Let me just jump over this because I'm running a little bit late over here and just say, yeah, lots of references, most of which are coming from people probably in the audience. And I will be happy to answer any questions.
Thank you very much, Professor Webb, for this fantastic talk. And we already have our first question coming from Matt.
Hey, Andy, what a great talk. So given, David Lurie's measurements, field cycled relaxation measurements, do you think that, there will be sort of an optimal field that people want to sit at to say maximize gray matter, white matter contrast? Or do you think the choice of magnetic field is always going to be, in these systems dominated by like magnetic field per dollar? Does it make sense to optimize for a particular contrast field-wise, or should we use things like fingerprinting and other ways, to get that contrast and then push to higher and higher magnetic fields?
Yeah, I think it's going to be so much application dependence, right? So if you look at if you're going to build a system, one of the nice things about low-cost MR is it's low cost. So you can build a hydrocephalus machine, and you can go and build something over here that's going to be used for pediatric brain growth, and you can go and build something else, right? Because I think those are going to be at different field strengths. If you're going to look for pediatric hydrocephalus, what do you want? CSF. So that if that's all you want, having a nice white matter, gray matter contrast, who cares? Doesn't matter, right? It's irrelevant. So you might choose your field there. If you're going to look at stroke, then it's something different, right? So if you're going to look at, T2 star things, and maybe you use contrast agents like certain people do, right, at low field, or you might decide here's the best field for this. So I think it may really get to that stage where you have very much application dependent situations and field strengths.
Yep. Thank you.
Great. So while people are typing, I'm just curious, Professor Webb, of your vision of when do you think we'll start seeing more low field scanners in countries that don't have any MR? When will this become more prevalent?
Well, you know, there's a current program by the Gates Foundation, which essentially has bought up, I think, 20 hyperfine units. And the idea is that 10 of those will go to different countries, initially in the African continent, and they will have a partner site, either in the US or in Canada or in Europe, and that people will start to work together, right, to operate those things, to develop those sequences, which are not currently on that system. So that, I think, is sort of the entrance point at the moment, but that's going to go to various, obviously, major sites there. And then we'll see what happens with that. You know, that's going to be, as I said, that's a lot of new units going in there. And I think that will really tell a lot about what is really the role of low field going to be. And learning from that, then, you know, we see one of our roles is also to have systems that are easy to train on, right? So hyperfine is great. It's a black box. Ours is complete opposite, right? So if you want to train people how to use it, if you want to train students how to build things, all of those kind of things, you have to have an open system there. And so I think that's the other part of it. We don't just want to sell systems there. You've got to have the entire infrastructure of supporting things, right? I mean, look at your groups there, right? You've got certain systems. It's not about buying the system. It's about having that infrastructure there to keep everything up and running and improving things. And, you know, that's what we aim at.
Great, thanks a lot. Next question from Jerry. Jerry, can you please unmute? If not on the minute, I think I have the question in front of me. So great talk, obviously. And how do you handle noise in an unshielded enclosure?
Yeah, we have various ways of trying to compensate for the noise. You know, there's a big history of noise in reduction in the log, in the Earth's fields. You know, when you're looking at oil wells, things like that. Hyperfine also, I know Matt knows better than I do, have about 5 or 6 different patents on that. So there are well-established ways of doing that. We're going to look at a couple of different ways. One of them is sort of analogous to looking at the dark modes of an RF coil, right? We're going to look at some of the modes where you're not picking up the MR signal, but you're actually picking up the external one. But it's actually going to be on the coil itself. So not external sensors there. It's going to be integrated as part of the coil, because there you're going to be really at exactly the same physical location as you're picking up the MR signal. I think the other ways, of course, of doing it are to have various antennas around your system over here, and then essentially to build a transfer function which says how does that contribute to the noise that is picked up by the coil, and then of course that can be just taken out in post-processing.
Thanks. Have you implemented any of that yet?
Ask me in about 3 days' time.
That's really quick work.
Well, I've been thinking about it a long time. It's just getting around to actually doing it. But yeah, we have some preliminary data that looks pretty promising. I know also in, I think, Clarissa or Larry's group that you've also been doing that as well. And I think that's sort of with external antennas. And of course, there are lots of ways just of let's say, oversampling the central case space and then, you know, doing various image subtractions that we can also look into. So I think there's a number of ways in the literature that should give good noise suppression.
And Andy, just to chime in, this is Matt. We have a paper currently under review that sort of opens the lid on the way our noise cancellation works. So hopefully that will be available soon.
Okay, good. That would be great.
Great, thanks a lot. So if anyone has any other question, please feel free to type. And one last thing for me, Andy. On the other side or the other edge of the spectrum, do you expect high field MR or 70 scanners to be more prevalent in places that can afford it?
Yeah, I mean, I think if you look at the Siemens 70, which is effectively the only program in town, is still expanding rapidly. I think there's 10 or 12 new ones go into the sites every year. So, you know, it's roughly one a month there. And that's limited more by production, I think, than people actually ordering. There's still quite a long lead time. I think what is going to be interesting to see is whether, as they go into not just academic hospitals, you know, such as your site or our site, but as they go into real sort of community hospitals, whether they can make an effect in terms of the standard of care, or whether they're just going to be in major centers and they sort of everybody goes in there, right? Like you might have like an MR Linux system. It's such an expensive system. You're not going to put that in every hospital. You're going to have one that is centered in Boston and one that is centered in New York, and then people will come in. So I think that's still the open question about how much of an everyday clinical utility it can be.
Great. Another question. Ranga, can you please unmute?
Great talk, Andy. Quick question. Which superconductor remains superconducting at 60 Tesla? That was my question.
Let's see. It's a good question. I should know the answer to that. I know that it's a pancake design that comes to the National High Magnetic Field Lab, and I actually don't know what it is. It's what they use in their pancake designs. I'm thinking it may be BISCO, but I'm not absolutely certain.
Okay. Yeah, the alloys that I know of, like they max out at 30 Tesla, I guess.
Yeah, I mean, they certainly make even higher fields over there, up to 100 Tesla, but often those are hybrid ones. So I'm thinking it's probably some form of BISCO. I don't think it's magnesium boride.
Okay. Okay. Great talk. Thank you.
Thank you.
Okay, so I think we're going to conclude with that. Thank you again so much, Professor Webb, for coming here today and giving us this fantastic talk. And we hope to see you in person very soon, hopefully.
Absolutely. Thanks very much all for the invitation.
Great, thank you. Bye, everyone.
Bye-bye.